Okay, this is going to be a really short little mini lecture on internal energy and really distinguishing between internal energy, heat, and temperature. So these are all things that we talk about, and I want to make sure that we're very distinct about which is which, especially as we move into the specific heat and latent heat and the law of thermodynamics, so that we are clear on our terminology. So internal heat is the sum of all the energy of all the molecules in an object, okay? It's also called thermal energy. So internal heat, that's the sum of all the energy of all the molecules within a substance, within an object, whatever we're talking about. So again, this is also called our thermal energy. Okay, so we've gone over this before, but just as a reminder, heat in general, remember heat is the transfer of energy. Okay, the transfer of energy due to a temperature difference. So it's the amount of energy that's moved due to a temperature difference. Okay, so that's what heat is. Temperature is a measure, I'll use a different color. Temperature, remember, is a measure of the average kinetic energy, if we think about it in terms of the kinetic theory of gases, measure of the average kinetic energy of the molecules. Remember, we talked about in that kinetic theory of gases mini lecture how temperature is related to the kinetic energy, so keep that in mind. So, and then thermal energy is the total energy of all the molecules, right? More molecules, more energy. So some quantity, I could have a brick of aluminum at a certain temperature, okay? And I could have another brick of aluminum that same temperature, and they have the same, together it's one temperature, but more energy, because now I have more molecules, okay? So little slight difference of these three items. Okay, so to get the total energy, then, we need to know the total number of molecules. So to get the internal heat, what do we need to know? Well, we need to know the number of molecules that are in our substance. Okay, so we need to know the number of molecules. Since it's the energy of all, and this energy is in kinetic energy, our internal energy, E internal, is equal to the number of molecules times the kinetic energy of a molecule. Okay? Well, remember, we learned that the kinetic energy of a molecule, let's do this in different colors so we can keep it straight. We know that the kinetic energy was equal to 1/2 mv squared. That was kind of that average value, right? That shouldn't be a little arrow, it should be just a line. Let's just make that clearer so it's consistent with what we've done before. And that was 3/2 kT. So that's in that kinetic theory lecture, so go ahead and check that out, which means that our internal energy is equal to N times 3/2 kT. And if we remember K is Boltzmann's constant. It's a lot of reminding here, a short little kind of connecting all the dots. And remember that Boltzmann's constant is equal to R, so the ideal gas constant, divided by Avogadro's number, right? R divided by Avogadro's number. And we've also defined this small n, I've got room down here, as the number of molecules divided by Avogadro's number. Remember? So that small n was the number of molecules divided by Avogadro's number, because we've used that in nRT. The number of moles is the number of molecules divided by Avogadro's number. That's the number of moles, small n. Remember? I'll write that down just as a reminder. And I want to give us that again because we've used different ways to represent the same things. PV equals nRT, right? We used it. We used that in terms of KT. PV equals, I'm going to lose the equation off the top of my head, but we've kind of been shifting between the way that we talk about things depending on the information that we have. So just to give another representative for our internal energy in terms of the number of moles, it is 3/2 nRT. So these are our representations of internal energy that we want to pay attention to. So kind of combining all of these pieces together, temperature, energy, heat, and now we're going to move into using it in the laws of thermodynamics. All right, good job.